All right, let's do share screen now. It's the usual thing here. All right, I think I've got some shade here. It's in the way. Here's what the problem is. Let's get that out of the way. Let me get this open up. Oh, let's see here. I want this photo. I'll lock it into place. Okay, how's that look? Yeah, so I'm going to start a little early just by reviewing some material before we get into new stuff. Just wanted to summarize some of the things we did with translation operators last time. We worked mainly in 1D. Define a translation operator by its action on the basis position eigncats. It just moves them over to a new location. The operator defined in such a way satisfies 4 properties, which are pretty easy to prove. They amount to the statement that the translation operators implement an abelian group, a commutative group. That's because translations commute with one another, as you see, or A plus B is equal to B plus A. And the operators themselves are unitary. Now, as we frequently do with continuous symmetries, we're particularly interested in the case in which the symmetry parameters are infinitesimal. We call those infinitesimal operations, although they're really just the identity with the infinitesimal correction added to it. So in this case, if the parameter A is small, where A is the displacement, then expanding things out to first order in powers of A, we get the identity at 0th order and then the first order correction. This operator K hat, which appears here, is essentially just a different notation for the derivative of T of A evaluated at A equals 0. The only thing we've done is split off a factor of I. And we do that really for conventional reasons. It's because we want to see this K hat operator to be Hermitian, because in physics, people like to see the generators and symmetries being Hermitian operators. And so that's what we've done here. That's the only reason for splitting off the I. The fact that K is Hermitian follows from the fact that the T operators are unitary. We call K the generator. Was there a question? We call K the generator of the translations because it gives the small correction needed in order to specify an infinitesimal translation. And we rely on the fact that finite operations, translations in this case, can be built up out of large numbers of infinitesimal ones. This is a common strategy or a common way of thinking about continuous symmetries. We'll see it again in this course later on. But in any case, for that reason, the K is considered the generator of the operations, the translations. The idea is that if you know what K is, notice that K is just a single operator. It's not parameterized by A or anything, because by its definition, it's this is derivative evaluated at A equals 0. So it's just one operator. But if you know what K is, then you know what the correction is for small translations. And then by composing those, you can build up any translations. So the idea is that all of the results of all of the content of the translation group is contained in just this one Hermitian operator. In any case, we took this infinitesimal relation and we sort of bootstrapped ourselves up by multiplying together large numbers of infinitesimal translations to get an expression for the T of A when A is not small. And that gave us an exponential formula here, which I want to box because it's actually an important formula. Let me put a box around here like that. Let me get the, yeah, like that. Okay, so this is the exponential version of the translation operator. And I think that's a summary of what we did the last 5 or 10 minutes of the last lecture. The action of the translation operator in a wave function is given here. It maps psi of x into psi of x minus a. And we also, at the end of the hour, worked out what the operator k hat does to wave functions. It basically applies minus I ddx to the wave function. This is still in one dimension here. All right, so that's a summary of what we did. Are there any questions about that before we proceed? All right, if not, then the first topic that I want to take up tonight is to basically generalize this to 3 dimensions. So let's work on that. Let's make everything 3D. I'll start here at the bottom of this page. I might as well. To make things 3-dimensional is fairly straightforward. It's mostly just notational. part of it is to generalize the position eigenkets to 3 dimensions. And we did that last time. We call those X here. This is really a simultaneous eigenket of the 3 components, X, Y, and Z, or X1, 2, and 3 of the 3 coordinate operators. It's assumed here that these operators commute with one another. Xi hat of Xj hat commutator is equal to 0. To be more careful about it, I shouldn't say we assume that this commutator is 0, nor is this a mathematical derivation of anything either. Rather, I think the right attitude to have about this commutator is that it's an experimental fact. As I pointed out in an earlier lecture, you can tell experimentally, but from the postulates of quantum mechanics make this apparent, that it's possible to determine experimentally whether operators commute. And it has to do with what happens when you have successive measurements one after the other, and whether or not the statistics depends on the order in which the measurements are made. So this should really be interpreted as an experimental fact. Now, I'm not saying people have gone out and done experiments to test this directly, but if this were not true, there aren't very many experiments that would agree with the theory if this were not true. In any case, this is a commutation relation for the position components of the position operator. Now, the translation operators are easy to generalize into 3 dimensions. The displacement is 3D. You act on an eigenket X of position, and it just maps it over to a new position. Kind of the obvious definition of the earlier 1D definition. Excuse me, the obvious generalization of the earlier 1D definition. And as we did with the 1D case, we can expand this out for small displacements. If we introduce the notation, let's call it hat sub I is equal to I times the derivative with respect to A sub I of T of A vector evaluated at A equals 0. That's the generalization of the single K we had in the 1D case. And what this implies then is that T of A, when A is small, is equal to the identity minus the vector, excuse me, it's minus I, get it right, it's minus I times the vector A dotted into the vector K hat like this, plus higher order terms. Now, in 3D, the translation operators, just as they do in 1D, in 3D, the operators commute with one another. T of A times T of B is the other way around, T of B times T of A. And the reason is that displacements just add when you do displacements. So addition is commutative. And what that means is, so all translation operators commute with one another. And in particular, that means that infinitesimal translations have to commute with one another. And that in turn implies that these generators, K hat, now there's 3 of them, you see there's a vector of generators, K hat sub I, that they commute with each other too. So you have K hat I, K hat J commutator is equal to 0. And this follows, as I say, from the commutativity of the translation operators. If I box my earlier commutation relations, we now see that the X's, now in 3D, we have 3 X's and 3 Ks. The X's commute with each other and the Ks commute with each other. All right. Now then, continuing on, I'll try to put it continuing onto a second page like this. Now, up above, I gave the action of K in 1D on a wave function. In 3D, it's just as easy to work it out. If I take hat sub I, the ith component of K, and let it act on a wave function and evaluate this at position X, it's the same thing as minus I times the partial with respect to Xi of psi of X. In other words, K hat I just turns into minus I ddxi, like that. And of course, the X hat itself, of course, is just multiplication by the corresponding X variable. Combining these two things together, we easily get a commutation relation for the X's and K's, which is that Xi Kj commutator is equal to I times delta Ij, like this. And if I box this, this is then the third set of commutation relations, which are still on the screen here. The 3 boxes here, 1, 2, and 3. And these give us a complete set of commutation relations amongst these 2 vectors of operators. And so that's more or less all there is to the 3-dimensional generalization. All right. Now, I think you can see here, because you have some education in quantum mechanics already, you can see here that there's arising the appearance of the momentum operator. So let's put this translation operator and this K operator stuff and this generators K on hold for a moment. And let's turn our attention to momentum. Let's start with momentum in classical mechanics, because there's some points that I want to make about that. So let's do classical mechanics CM. Here's what that means. And let's look at the momentum in classical mechanics. So it turns out there are actually two different definitions of the momentum in classical mechanics, and it'll be important to distinguish between them. The first definition comes from elementary physics. It's a momentum is the mass times velocity. This is what you get in physics 5A or in high school physics. On the other hand, if you're taking physics 105, they give you a different definition, which is the momentum is the derivative of the Lagrangian with respect to the velocity. And of the first of these, we'll call this the kinetic momentum. And the second one we'll call the canonical momentum. And the question is, are they the same? And the answer is, it depends on what the Lagrangian is. So let's look at some Lagrangians. So Lagrangian, a typical Lagrangian, has got the kinetic energy, mv squared over 2, minus the potential energy, minus v of x. That's probably what you've seen in 105 type courses. On the other hand, if there's a magnetic field around, there's an extra term here, which is q over c times the velocity dotted into the vector potential, which the vector potential can be a function of x and t. By the way, the potential can also be time dependent as well. We can have time dependent potentials like that. I've just wrote x here, but it might also depend on time. Well, in any case, this is the Lagrangian for a particle moving in a scalar potential as well as possibly a magnetic field. If we now apply the definition of the canonical momentum as dl dv, you can see that coming from the kinetic energy term, we get mv, which is the kinetic momentum. But if there's a vector potential around, there's another term too, which is q over c times the vector potential itself. And so the canonical momentum differs from the kinetic momentum in the case in which there is a vector potential. Now, in this course, we're going to give a fair amount of attention to problems with magnetic fields, so it's going to be important to distinguish these two. If you never deal with magnetic fields, you don't have to worry, these two are the same. But in any case, we will pay attention to this. So these are different definitions if A is non-zero. Now then, there's various questions you can ask to compare these two momenta. You know, one question is, which one is more physical? The answer is the kinetic momentum is more physical because it's just related to the velocity of the particle, which you can measure. Whereas the canonical momentum involves the vector potential, which again could depend on time here. I left that out, but I could put it back in. The canonical momentum involves the vector potential, and the vector potential is not unique, but rather is subject to a gauge transformation. That's to say, the vector potential is partly conventional. And so for that reason, that canonical momentum is not by itself directly physical. You can't really go measure it unless you know what gauge you're working in. It's more of a theoretical construct. So now one question is why would anybody ever use this canonical momentum? And the answer is that you need to use it in order to do Lagrangian and Hamiltonian mechanics. And that's because this canonical momentum here is what has to appear in going through the transformation from Lagrangians to Hamiltonians. All right. I'll say more about gauge transformations and so on in classical and quantum mechanics later on in this lecture. But in any case, this is the difference between these two types of momenta. Now, the momentum plays different roles in different contexts. One of them, an important role that it plays, is that it's the generator of translations. A moment ago, I was talking about generator translations in quantum mechanics. Now let's do something similar in classical mechanics. Let's suppose I'll do this in 1D now, just for simplicity. Let's suppose I've got a function of x and p for a particle moving in one dimension. This is what you could call a classical observable. It could, for example, be the energy of the particle, kinetic plus potential or something. In any case, let's suppose we have this, and let's define what I'll call a classical translation operator, T classical of A. And it acts on the function f, and what it does is it just shifts x and leaves the momentum alone. For example, if this were a distribution function of particles, it would mean you'd move all the particles but leave their momentum unchanged. So, I'm sorry, I didn't write this right. Let me write it correctly. T classical of A applied to a distribution function f evaluated at x and p is equal to the original distribution function evaluated at x minus a and p. And this just means, as I said, you shift the particles, their positions, but leave their momenta alone. All right. Now, if a is small, we can expand this out and write this as f of x comma p plus a times partial of f with respect to x, which I think is fairly obvious to first order anyway. But partial of f with respect to x can also be written this way. It's f of x comma p. And the correction term can be written this way as plus a times the Poisson bracket. Let's see, this should have been a minus sign here. Plus a times the Poisson bracket of the momentum with the function f plus higher order terms. If you use the definition of the Poisson bracket, you'll see that this is equal to, with a minus sign, minus df dx. So it can be written like that. Now, I don't want to go too deeply into the theory of classical mechanics and its canonical structure and so on, but let me just say that this fact is what in classical mechanics qualifies or usually makes people understand, a way of understanding of saying that the momentum is the generator of translations, because it gives rise to this correction term for the infinitesimal translation in classical mechanics. So the momentum plays the role as a generator of translations. This has an impact on symmetries and conservation laws, still in classical mechanics. Symmetries are generally related to conservation laws. This is one of the main reasons that we're interested in symmetries all over the place in quantum mechanics. So in a simple manner, how it works in classical mechanics is to say that if you have a system in which the Lagrangian is invariant under translations, then it really means the Lagrangian is independent of x, is what it means. Then the momentum is conserved. Well, this follows from the Euler-Lagrange equations. The Euler-Lagrange equations say that the time derivative of the momentum, this is the canonical momentum defined in this way up here, dl dv, is equal to partial of L with respect to x. But if L is independent of x, this is equal to 0. And thus we see the momentum is conserved. So this is an example of what's called Noether's theorem, general relationship between symmetries and invariants. But please note, it's not the kinetic momentum, but it's rather the canonical momentum that's conserved, at least if it makes any difference. That's what it's going to be. It's going to be the canonical momentum. All right. So that's kind of a end of a digression into classical mechanics. And let's now go back to quantum mechanics. In quantum mechanics, we had this operator k hat, which played the role of, in 3D, it was a vector. So I'll write it as k hat with a vector on. By the way, hat does not mean unit vector. It means operator here. And to say it again, I'm using these hats on operators really only in the case that I think there's some danger of confusing it with a classical object or a quantum number, which is a C number. If you wanted to, I could write hats on all the operators, but that gets kind of tedious. So anyway, this is the k-hat operator that came from our theory of translations. And that in quantum mechanics is the generator of translations. But in classical mechanics, the momentum is the generator of translations. Now, in quantum mechanics, the momentum operator, there should be a momentum operator because the postulates say that every measurement corresponds to an operator, every measurement process. So we can certainly measure momentum, and therefore there must be a momentum operator. Let's call it p hat, like that. We don't actually know what it is yet, but since momentum plays the role of the generator of translations in both classical and quantum mechanics, it's a guess that these two things are related to each other. They're both free vectors. Unfortunately, they can't be equal to each other because the dimensions aren't right. P has dimensions of momentum and K has dimensions of inverse length. And therefore, let's guess that the quantum operator corresponding to measurements of physical momentum is proportional to K hat with a proportionality constant, which must have dimensions of action in order to make the dimensions come out right. Let's call that constant H bar. We put it in there like that, and we get this relationship. Now, giving us, it's really a guess, if you like. It's a guess for what the momentum operator in quantum mechanics should be. We guess it's related to the generators of translations in this manner. All right. Now, if we do this, then we can take our earlier commutation relations involving x's and k's and translate them into commutation relations involving x's and p's. And if we do, we have xi xj commutator is equal to pi pj commutator. And I'm putting hats on it to emphasize these are operators, which are 0. And we have xi hat with pj hat commutator is equal to IH bar delta IJ, like so. And these are, of course, the standard commutation relations among position and momentum in quantum mechanics. They're otherwise called I call them anyway, the Heisenberg-Born commutation relations. Heisenberg and Born both played a role in this. I understand that Born had engraved on his tombstone the commutator between X and P, as that being IH bar. Actually, he didn't have H bars in those days. He had H bar was H divided by 2 pi. In any case, he was so proud of having discovered that fact. All right, anyway, these then become the Heisenberg-Born commutation relations. All right, now the value, the quantity H bar here is a dimensional quantity in the way that I've introduced it. So it has a number that depends on the units. And if you wanted to know what its value was, you'd have to do an experiment to find out. In fact, people do that. This is, of course, relative to our standards or our units for measuring momentum and length and so on that are contained in K. In any case, one of the consequences of the position momentum formalism, which emerges from this, which I'm not going to go over in detail because you've seen it already in your earlier course, but one of the consequences of that is that an eigenstate of momentum, of course, is a plane wave. It's e to the I p dot x over h bar, where the p now without the hat is the momentum eigenvalue. And this implies that there's a wavelength, what we call the de Broglie wavelength, which is 2 pi h bar divided by the magnitude of the momentum. And so experiments that involve free particles or particles that states of free particles that approximate eigenstates of momentum can be used to determine the de Broglie wavelength. And from that, from the known momentum, you can determine what h bar is. So this is, at least in principle, is an experimental method for determining the value of h bar. All right. Cummins' book has a nice discussion of interference experiments that are carried out with neutron beams with silicon interferometers. And some of these experiments are extremely beautiful with what they did. They get Bragg diffraction angles that are incredibly small. I recommend that you read that section in Cummins' book if you want to see some beautiful experimental results. Anyway, those experiments fully confirm these commutation relations and the notion of the de Broglie wavelength and so on, interference between waves. All right, so that is the way of introducing the momentum into quantum mechanics. I'd like to call your attention to a particular formula, something that arises in some situations as a matrix element looks like this. We've got X on the left, meaning we're looking at a wave function. We've got a component of the momentum operator, let me call it P sub I in the middle, and then a state psi on the right-hand side. If you think about what this means, we've got a state vector psi. We're going to let the momentum operator act on it. And by putting the X on this side, we're asking for what is the wave function of the result. And based on what I've said so far in regard to the K hop, P is just H bar K. So this becomes minus I H bar times partial with respect to Xi applied to the wave function psi of X. But psi of X is the same thing as the scalar product of X with psi. And let me kind of put a box around this equation just to draw your attention to it, because what it shows you is it's part of the collection of rules we have for converting from Ket language into wave function language. It says if you have a momentum operator inside a matrix element like this with X on the left, you can bring it out if you want, as long as you replace it by the minus I H bar ddxi like this. There's just a rule that's useful. All right. So this is position and momentum. So this is the setup of the position momentum representations, the transformations between them using Fourier transforms, the representations of the operators in both position space and momentum space wave functions, uncertainty principles, uncertainty relations, delta x delta p is greater than h bar over 2, minimum uncertainty wave packets, and a whole collection of topics like that, which are covered briefly in the notes and which I'm not going to cover in lecture because you've seen them before already. So if you need a review on that, read the notes anyway, it's not that hard. And if you have any questions about them, feel free to ask me about them in office hours or by email or something. But I think I'm going to skip them in lecture because presumably you've seen them already. And instead, what I'd like to do is to finish this subject of spatial degrees of freedom and move on to a new topic, which is that of the time evolution in quantum mechanics is our new topic. Are there any questions about the spatial degrees of freedom in this formalism before I move on to the next topic? All right. If not, then let me push the old page out of the way and we'll start a new page. So the next topic, as I say, is the time evolution in quantum mechanics. Let's suppose we have a system, of course, that corresponds to a Hilbert space E according to the postulates. Let's suppose we have a system, and let's suppose at some initial time, the system is in a pure state, which I'll call psi at t0, like this. I didn't write this very well. Let's do it again. This is psi evaluated at t0. This is the pure state, we assume it's a pure state at the initial time t0. And at a later time, the system is in a state psi of t. And we will postulate that these two states are related by a linear operator. That is to say, we'll postulate that the time evolution in quantum mechanics is governed by a linear operator. We call this operator U, and it has to be parameterized by both the initial and the final time. So I'll write it as U of t comma t0. So this is a postulate. In fact, it's a new postulate, which we can add to the 6 that we've had already. We can call it postulate number 7. And this is the basic content of it. Now, this operator U has certain properties, of which there are 3 that I want to point out, properties of U. The first one is that if the initial and final times are equal to each other, then U has to be the identity because there was no evolution. That's fairly obvious. The second property is that the U operator for all values of t and t0 shall be unitary. So its inverse is equal to its Hermitian conjugate, like this. The reason we require this is because we want probabilities to be conserved between the initial and the final time. If you have a probability of finding the particle in anywhere in space is equal to 1, which is logical because that's what it ought to be, at the initial time, then as long as you're not creating and destroying particles, you ought to have a probability of 1 also at the final time. And so that's an example of what we mean by preservations of probabilities. Now, I'm not sure how clearly I've stated this in previous lectures, but if you have an operator which preserves all scalar products, if you're in finite dimensions, that implies that the operator is unitary. I'm not sure if I have given or will give a homework problem on that, but it's not hard to show. In infinite dimensions, you need to show something else as well. You need to show the operator is invertible. If it's invertible and it preserves all scalar products, then it's unitary. In any case, it's the preservation of scalar products, which means probabilities, which is why we require the time evolution to be unitary. The third property is the following, that if I take U between 2 times t2 and t1, and then I multiply that by U evaluated between t1 and t0, the answer is equal to U evaluated between t2 and t0. Notice that in this formalism, the time on the right is the initial time, and the time on the left is the final time. That's just the notation I'm using here, but it's convenient to do it that way. And what you see here is that this U operator maps us from t0 to t1. And the idea is that if you apply this to a state, you're kind of you're advancing the state to its value at some intermediate time, t1. And then you take that time as initial conditions for a second phase of the evolution that takes you from t1 to t2. And the answer is going to be the same as going directly from t0 to t2 without stopping in the middle, in effect. This is the content of property number 3. And this is called the composition law, which is necessary for the consistency of the time evolution theory. All right, so these are the properties of the unitary time evolution operator, according to postulate 7. All right. Now then, as we did with translations, which are, of course, amount to advancing operators, advancing states of a system in position, moving their position variables, these operators U advance things in time. So there's kind of a space-time trade-off here. It reminds you of relativity theory. As we did with translation operators in space, we're going to do also here and consider what happens when the time increment is infinitesimal. So because infinitesimal operations, once you know them, you can build up finite operations by composing the large numbers of infinitesimal operations. It's the same philosophy. So let's look at two times, one of which is t plus epsilon, and the final time is t plus epsilon, initial time is t. If we expand this in a Taylor series, we get the leading term is u of t comma t. And then the next term I'll write this way is minus I times epsilon times omega of t, plus there's plus higher order terms, where omega of t is defined this way, its definition. It's equal to I times the derivative with respect to t prime of u evaluated at t prime comma t. So we take the derivative with respect to the final time, and then we evaluate that when the final time is equal to the initial time. So this is just a definition of this operator omega of t here. Omega is a function of time because the right-hand side here depends on time. It depends on the t. The t prime dependence disappeared because we evaluated at t prime equals t. But the dependence on the initial time t remains, and so omega in general does depend on the initial time t, and that's why I'm putting that in there. Omega is an operator, and so to emphasize that, I'll put a hat on it, even though maybe I don't need it. But anyway, it's an operator. Now, omega in quantum mechanics is logically called the generator of time translations because, as before, it's what gives us the infinitesimal correction away from, oh, by the way, this leading term is the identity because of property number 1 up here. So it gives us the infinitesimal correction to the identity for a small time increment. And as I keep saying, if you know that correction, then you by composition, you can create time evolution operators for finite time differences. All right, so we consider omega then to be the generator of time translations in quantum mechanics. All right. Now allow me to switch back to classical mechanics again, because in classical mechanics, the classical Hamiltonian is regarded as the generator of time translations. And I'd like to now show you why that's considered to be true in classical mechanics. Let's suppose I have a classical Hamiltonian h of x and p. I won't put any hat on it because this is classical now. And let's suppose I've got a classical observable f of x and p like this. Again, it could be the energy or angular momentum, anything. And this classical observable acquires a time dependence because the x and the p parameters of the particle are evolving along the orbit. So I can write this as f of x of t comma p of t like this, and define this as f of t, meaning this is how f evolves as a function of time along an orbit. Now, if you want to know the rate at which f evolves along an orbit, we can use the chain rule and compute df dt. That gives us partial of f with respect to x times x dot plus partial of f with respect to p times p dot. Now, by Hamilton's equations, however, x dot, I'll copy the df dx here. By Hamilton's equation, x dot is equal to dh dp. And then I've got the df dp over here. And by Hamilton's equations, p dot is minus dh dx. So I put that in like that. And what you see appearing here now is a Poisson bracket of f with the Hamiltonian h. And so if I put this together, then what we have is that f of t plus epsilon, let's write it this way, is equal to f of t plus epsilon times the Poisson bracket of f with the Hamiltonian h. And then, of course, there's higher order terms. And as I say, this is all purely classical mechanics. But like what we did earlier with momentum, this is the justification given within classical mechanics for regarding the Hamiltonian as a generator of time translations. And by the way, there's once again a relationship between symmetries and invariants. If the Hamiltonian is independent of time, then the Hamiltonian is conserved. The energy is conserved, and the Hamiltonian is independent of time. That's the analog of the conservation momentum law that I spoke of earlier. Now, in view of these facts in classical mechanics, it's logical that while we've got this operator omega hat of t, which is the generator of time translations in quantum mechanics, it's logical that it should be related to the Hamiltonian operator in quantum mechanics. I'll put a hat on it here. This, of course, is not the same as the classical Hamiltonian that appears a few lines above. That's why I'm putting I'll leave the hats off of classical Hamiltonians and put them on for quantum, because here the distinction is important. Now, we haven't defined what H hat is yet, but by the postulates of quantum mechanics, it ought to be the operator that corresponds to measuring energy. And so there's then, given that we can measure energy, then the question is what operator corresponds to that. And what's emerging here is that it's a good guess that it's some analog of the classical Hamiltonian. However, the two can't be the H hat, which is a generator of time translations in classical mechanics. So all this logic suggests that there's a close relationship between H hat and omega hat, but they can't be equal because they don't have the right dimensions. H has dimensions of energy and omega has dimensions of inverse time. So let's just guess that they're related by a proportionality factor, which has to have dimensions of action. And that means that it has the same dimensions as H bar. And we'll guess, in fact, that it's even the same H bar that appeared in the momentum equation. In fact, we better require that it's the same H bar that appeared in the momentum equation, because the earlier momentum equation and this energy equation, which is appearing here, are obviously space and time components of an energy momentum 4 vector. And if you're going to do relativity theory, the only way you can make the four vectors of operators be related to one another is to have the proportionality has to be the same for all 4 components. So let's just say that relativistic covariance, which we're not bothering ourselves with at this point, but it certainly is a valid physical principle, relativistic covariance requires that the H bars all be the same. Okay. So this then gives us then a definition of the quantum Hamiltonian in terms of the generator. And what it means then is that U of T plus epsilon comma T is equal to the identity 1 minus I epsilon over H bar times H hat of T, like this, plus higher order terms. This is the earlier version of the expansion of the unitary time evolution operator for small time, now expressed in terms of the quantum Hamiltonian. All right. Now, given the, I think that was something I wanted to do earlier and I didn't do. Anyway, I'll leave it for now. Given the importance of U, it's important to work out a differential equation for U. That's the next project. That's to say, let's consider the derivative of U of T comma T prime, or let's T comma T zero, let's say it that way, with respect to the final time T. Let's consider this derivative. Now here I'm not assuming that T is close to T0, but we can use the definition of a limit and write it this way. This is the limit as epsilon approaches 0 of U of T plus epsilon comma T0 minus U of T comma T0 divided by epsilon. That's the definition of the limit. On the other hand, by the composition rule, U of T plus epsilon comma T0 can be written this way as U of T plus epsilon comma T times U of T comma T0. I hope I'm not writing that too small. I hope you can see that. What I've done is, you see, I've factored out a U of T comma T0 to the right. That's the same factor as you see down below in the line below. So this whole thing can be written this way now as a limit as epsilon goes to 0 of U of T plus epsilon comma T minus 1 over epsilon, that whole thing multiplied times U of T comma T0. Let's write it like that. Now then, this limit that appears here, well, the U of T comma epsilon comma T, this is given right up above here. It's 1 minus I epsilon over H bar times H. So we subtract the 1 here, and the epsilon denominator will cancel that. And the net effect of this is that the partial with respect to T of U of T comma T0 is equal to minus I over H bar times what's left over, which is H hat of T times U of T comma T0. And as far as the minus I over H bar, I'll bring it over to this side and make it as IH bar over here. And having done so, what we end up with is a differential equation for the unitary time evolution operator. So we can either think about U as being developed by the composition of a large number of infinitesimal unitary time evolution operators, multiplied together, or we can think of it as a solution of this differential equation, in which the initial condition, by the way, is that u of t0 comma t0 is equal to 1. That was one of the requirements that had to be satisfied by our u operator. This equation that I've written down here is a version of the Schrodinger equation. It's a Schrodinger equation for the unitary time evolution operator. If we apply that operator to the, let me do it right. If we take the state vector at the initial time t0, and we apply this unitary time evolution operator to it, then we know what we get is that we get psi of t at the final time. That was the original definition of this u operator here. If I now differentiate both sides, IH bar ddt on psi, the IH bar ddt acts only on the u. The psi of t0 doesn't have any t dependence. It acts only in the u. And for that, I can use the u equation up here. So I replace this by hu, but the hu, then the u multiplies psi of t0 and gives me a psi of t. And so the result is that IH bar d psi dt is equal to h hat of t times psi of t, like this. And I'll box this because this is another version of the Schrodinger equation, probably more familiar because it now deals with state vectors instead of operators, but they're trivially related to one another. And this is the version of the Schrodinger equation in terms of state vectors. Now, in a sense, the Hamiltonian has no more information in it than the U operator does. And we took U as this starting object we started with in this presentation, starting with a postulate, and we kind of derived H from it. So we're kind of going around in circles in a way, which comes first, H or U? It's a matter of preference. But of course, in practice, we oftentimes know H and we want to derive U. And if so, it means solving this equation or this equation down here, solving the Schrodinger equation in some version or another to find U. If you were given U, you can get H by differentiating. That'd be enough to do it. All right. Okay. So this is the introduction to the Schrodinger equation. Now, I've been writing this Hamiltonian H as a function of time without explanation. It really came from up here, is that the omega was a function of time. But even in classical mechanics, if I can go back to that, where we were doing that's right up here, even in classical mechanics, this H here oftentimes depends on time. As I say, depends not only on x and p, but also on time t. As I say, I have time-dependent Hamiltonians. And let me make a comment or two about what that means in practice. In practice, a time-dependent Hamiltonian usually means that you have fields that are time-dependent. For example, suppose I've got a parallel plate capacitor, but I drive it with an AC current like this, and I've got some charged particle which is sitting in the middle. So the particle is going to move up and down as the AC electric field moves up and down. If this is the case, we can write the scalar potential for the particle, a psi of x and t, is given by some spatially independent potential phi of x like this times cosine omega t. At least this is one possibility for modeling the electrostatic potential, time-dependent potential that exists in the region between the plates. So if you put this into a Hamiltonian, you'd want to multiply by the charge of the particle to get the potential V. That would become a function of x and t as well. So this is a simple example of how you get time-dependent potentials and more generally time-dependent Hamiltonians. Another example is if you launch a spacecraft like the Mariner was the first ones they launched back in the 70s, out through the solar system, they like to get gravity boosts. They like to set it up so you get gravity boosts from the planets. The idea is this: you've got a great big lumbering Jupiter that goes in its orbit around the solar system, and the little spacecraft comes floating by. And the spacecraft has so little mass that it doesn't affect the orbit of Jupiter very much at all. So what Jupiter does in its orbit and going around the sun is it creates a time-dependent gravitational field, which the satellite moves in. And by using that time-dependent field, it's possible to gain and or lose energy, depends on the orbits and so on, but gain energy is the object here. It can gain energy in the time-dependent field. Time-dependent Hamiltonians mean if the Hamiltonian has an explicit time dependence, it means energy is not conserved. And that's exactly what's used in getting the spacecraft to be ejected from the solar system. Well, in any case, this is what's meant by time-dependent Hamiltonians, and that's what appears up here as well. However, in many, many practical situations, our Hamiltonians actually are time independent. And if that's the case, then the Schrodinger equation up here simplifies some. So let's take a look at it in the case where h is independent of time. So you've got IH bar partial of u with respect to t, which depends on the 2 times t and t0, is just equal to h hat, which is now independent of time, times u of t comma t0. And let me move some pages up to make some space here. And in that case, it's easy to solve the equation for the, it's easy to solve the equation for the unitary time evolution operator. The solution is that u of t comma t0 is, of course, the initial conditions here are u of t0 comma t0 is equal to 1. Anyway, the solution with those initial conditions is that this is equal to e to the minus I quantity t minus t0 times the Hamiltonian divided by h bar. So what we see is that in the case that the Hamiltonian, in the important special case in which the Hamiltonian is independent of time, then the time evolution operator depends actually only on the elapsed time, not on these 2 times independently. If that's the case, we can take t minus t0 by a change of notation, just call it t, which we now reinterpret as not as the clock time at the end of the interval, but rather as the elapsed time. Or if you like, we can set t0 equals 0, means the same thing. And then what we have is we have a useful formula for time independent Hamiltonians, which is that u of t is equal to e to the minus I t h hat over h bar, like so. We get this oftentimes useful result for the expression for the unitary time evolution operator in cases in which the Hamiltonian has no explicit time dependence. All right. Maybe I should pause here and ask if there's any questions about this basic setup of the time dependence in quantum mechanics before I go on. All right. If not, then I want to move on to the next topic, which is the Heisenberg picture. We've been implicitly up to this point in this course using what's called a Schrodinger picture without saying so. In the Schrodinger picture, the state vectors, so this is a Schrodinger picture, the state vectors depend on time and the operators don't. Or more exactly, the operators might have a time dependence, but if they do, it's what we call an explicit time dependence. That's the only time dependence that you have in the Schrodinger picture for operators. In fact, this example of the potential in the capacitor plates, which we had just a little minute ago, here it is again, where the potential energy depends on time. This is an example of an operator. It's an operator because it's a function of x, which is an operator. It's a multiplicative operator in wave functions, but still it's an operator. It has what we call an explicit time dependence, in this case because of time-dependent fields. And that's normally where explicit time dependence comes from. On the other hand, many operators like position, momentum, and so on don't have any explicit time dependence. Anyway, in the Schrodinger picture, if an operator has a time dependence, that's all it has, is just explicit. Let me put an S subscript here to indicate this is in the Schrodinger picture like so. In the Heisenberg picture, on the other hand, the state vectors have no time dependence, but the operators always do. Whether or not the Schrodinger operator has an explicit time dependence, the Heisenberg operators always have a time dependence. In effect, what's happened is that going from the Schrodinger to the Heisenberg picture, the time dependence which occurs in the state vectors has been shifted over to the operators like this. So that's the general overview of the two pictures. In detail, it works like this, is that the Heisenberg state vector psi h is given by the unitary time evolution operator u of t comma t0 dagger applied to the Schrodinger state vector psi s of t, like so. Now this U operator without the dagger moves us forward, moves the Schrodinger vector forward in time from t0 to t. So with the dagger, it reverses it, moving us from t back to t0. So this is the same thing as psi Schrodinger evaluated at the initial time. The state vector in the Heisenberg picture is the same as a Schrodinger vector at the initial time. And therefore, this Heisenberg vector does not depend on time, it's constant. Operators in the Heisenberg picture, on the other hand, it means Heisenberg, the operator in the Heisenberg picture, is given by our U operator, U of t0 dagger, applied to the Schrodinger operator, which may have a time dependence, even though usually it doesn't, and then a u of tz0 on the other side. So it's conjugated by u, basically. That's what the u operator, which converts from Schrodinger into Heisenberg picture. Now, these are just definitions of the operators in the two pictures. Now, in the Schrodinger picture, of course, we have a Schrodinger equation for the state vector. That's what we've just been talking about. But in the Heisenberg picture, there is no Schrodinger equation with the state vector because it doesn't evolve. On the other hand, there has to be an equation of motion for the operators because they do evolve. So let's work out what that is. Let's work out the IH bar ddt of the Heisenberg operator A Heisenberg as a function of time. This just involves applying the chain rule to these three terms that you see on the right-hand side. So let me write them out. I tell you what, I'll do it this way. I'll take the last term first. It becomes U dagger times A Schrodinger, and then I have IH bar du dt, the u dt like this. And then I'll take the derivative of the first term, it becomes in plus IH bar ddt of u dagger times A Schrodinger times u. And then we'll take the middle term and we have u dagger and IH bar dA Schrodinger dt like this and a u like that. All right, that's just brute force chain rule. On the other hand, this IH bar du dt here in the first term, by the Schrodinger equation for u, that's the same thing as h times u. And the h is, of course, in the Schrodinger picture. I can put that in to make it explicit, but that's what it is. It's in the Schrodinger picture. Likewise, in the second term, this IH bar ddt of u dagger, this is basically with a minus sign, the dagger of what you have up here. This becomes minus u dagger times h Schrodinger. H Schrodinger is Hermitian, so I don't have to dagger it. But that's what appears there. So if I write this all out, the first couple of terms look like this. It looks like u dagger, A Schrodinger, H Schrodinger. I'm bringing this whole thing down here like this and working on the first term, and then times u. Then we have minus u dagger, H Schrodinger, A Schrodinger, u. And then we've got the last term, which I'll come back to in a minute. It's right here. As far as these first two terms are concerned, let's insert a u dagger between the two Heisenberg operators, between the two Schrodinger operators, u dagger like that. If we do, then you see the appearance of u dagger, A Schrodinger, u. Well, that's the same thing as A Heisenberg. And then you have u dagger, HS, u. That's the same thing as H Heisenberg, the Hamiltonian, the Heisenberg picture. The second term has got the two operators in the reverse order like this. And as far as the last term is concerned, let me just put as last, I'll fill it in a minute. We see the first two terms give us a commutator. And so the result is, the resulting equation looks like this, is IH bar dA Heisenberg dt is equal to the commutator of A Heisenberg with the Hamiltonian in the Heisenberg picture. And as far as the last term is concerned, you can see that it's IH bar times the derivative with respect to time of the Schrodinger operator, which would be 0 if there's no explicit time dependence, but sometimes there's non-zero. And then conjugating by u dagger converts it into the Heisenberg picture. So let me write it this way, as IH bar dA Schrodinger dt, like so, with parentheses like that and an H subscript. And that means compute the time derivative in the Schrodinger picture and then convert in the Heisenberg picture. That's the meaning of that formula. All right, so let's write this out. All right, so these then are called the Heisenberg equations of motion. Heisenberg equations of motion. And they take the place of the Schrodinger picture when you're working in the Heisenberg picture. These, as you can see, are equations of motion for operators and not for state vectors or not for wave functions or operator equations. You had some experience already in that first homework exercise with differential equations involving operators, and now they appear in a bigger way here, much bigger way. The Schrodinger picture and the Heisenberg picture are physically equivalent. I'll say more about that in a minute. Doing it one way or doing the other makes no difference physically, although the formalism you go through to get the answers can be quite different. I'm going to try and see if I can make this a little brighter. Good, that worked. So I'll get back to that in a minute, but you have your choice about which of these two pictures you want to work in. One obvious, so there's pros and cons. One of the cons of working in the Heisenberg picture is that these are operator equations. And as you can imagine, dealing with differential equations of operators is harder than working with differential equations of wave functions. And operators kind of lives in a bigger space is kind of the idea. In spite of that, there are certain problems for which the Heisenberg picture is easier to work with than the Schrodinger picture. For example, it gives you very nice results very quickly in the case of the harmonic oscillator. It's also important for theoretical reasons as well. For example, in quantum field theory, relativistic quantum field theory, you're interested in the covariance of the theory. It has to look the same in all Lorentz frames. And the Lorentz covariance is expressed most simply in the Heisenberg picture, because it treats space and time on an equal footing. Yet another thing where theoretical considerations are important is that the Heisenberg picture is generally closer to classical mechanics than is the Schrodinger picture. And let me just make a few comments about that. Earlier, I explained to you that if you had a classical observable f and you considered its time derivative along an orbit, then the formula could be given this way, as the df dt could be written this way as the Poisson bracket of f with a Hamiltonian. This was assuming we had a function f of x and p. If we allow our function to depend on time, that is to say, to contain an explicit time dependence, then there's an extra term here, which is partial of f with respect to t. So this in classical mechanics is the general expression for the rate of change of a classical observable along an orbit, a Poisson bracket with a Hamiltonian plus this derivative with respect to explicit time dependence. And if you compare this to the Heisenberg equations of motion, you see they have the same structure. In fact, what you can see here is that Poisson brackets in classical mechanics are being, in a certain sense, replaced by commutators. Really, it's really the correct statement would be is that the commutators. Let's see, I'm worried here about my IH bars. This should be right. I'll worry about that later. Let's just say that to within a factor of IH bars is that Poisson brackets and commutators go into one another in some kind of classical quantum correspondence. This is a correspondence that was noticed by Dirac in the very earliest days of quantum mechanics, and it was used to establish the formal structure of quantum mechanics partially on the classical model. All right. Yeah, the commutator can be roughly thought of as being like IH bar times a Poisson bracket, because if I just formally replace this square brackets by H bar times a curly bracket, then I could cancel the IH bars and it would look just like this equation. This is kind of hand wavy because we're replacing operators by classical or C number objects, but nevertheless, the rules that I'm laying out here do have some foundation. All right, so those are some of the aspects of the Heisenberg picture. All right, Heisenberg equations of motion. I want to say something about the physical equivalence of the two pictures. This has to do with time evolution. The two pictures only differ in respect to time evolution. If you look at them at the initial time, they're really the same. There's no difference at a fixed time, but the time dependence is different in the two pictures. In speaking of time dependence, we are oftentimes, well, in speaking of measurements of any kind, we're oftentimes interested in matrix elements that look like this, a state phi, an operator A, and a state psi. It's basically a matrix element of some operator. In fact, all physical measurements can be expressed in terms of the absolute value squared of such matrix elements. And in particular, if we're talking about the time evolution of those measurements, in the Schrodinger picture, you'd normally have A be time independent, and the state vector psi and phi would depend on time. Let's look at this first in the Schrodinger picture, like this. In fact, to be more explicit about it, let me write it this way: as phi Schrodinger, which is a function of time, and I'll write A Schrodinger, which I'll allow to be a function of time because it might have an explicit time dependence, and then psi Schrodinger is a function of time. Now, if I relate this to using the definition of the Heisenberg picture, psi Heisenberg here as a psi Schrodinger of T is given by, as a bra, is given by, let me say it right. this is a phi. Phi Schrodinger is a function of t and written as a bra is given by the Heisenberg thing here multiplied times the U dagger operator. The A Schrodinger I'll keep the same like this, which is a function of time. And then the psi Schrodinger over here is the same as the U times the Heisenberg state like so. And if we do this, you now see the appearance of the Heisenberg operator in the middle. And so we get phi Heisenberg sandwiched around A Heisenberg, which is a function of time, and psi Heisenberg on the left. So the statement here is that the Schrodinger expectation value and the Heisenberg expectation values are the same. There's no difference between the two.
So the Heisenberg operator, can it have implicit time dependence as well? Or is that also only explicit?
Yeah, so the distinction between implicit and explicit time dependence is easiest to understand in classical mechanics. If I go back to my classical formula here, the partial of f with respect to t here refers to that explicit time dependence over there. This is like the cosine omega t for the potential in the capacitor plates. Whereas what they call the implicit time dependence comes from the fact that the x and the p upon which f depends are themselves functions of time along the orbit. That's what they meant by implicit. And so that's captured in this Poisson bracket. So in the classical context, this part is the explicit time dependence, and this is the implicit. So by analogy, in quantum mechanics, we would call this the explicit time dependence, and what comes from this commutator, you'd call that the implicit. If you like, this is related to those UU daggers that have been stuck in there. Does that answer your question?
Yes, it does. Thank you.
Okay, good. All right. Now, all right, good. So that's some of the basics of the Heisenberg picture and the Heisenberg equations of motion and their physical equivalents. Now, so far we've been talking about Hamiltonians, but we haven't actually said what any Hamiltonian is. On the other hand, it's clear that the way we developed this, that the quantum Hamiltonian is a generator of time translations, is the structure was set up on the analogy of classical mechanics, in which the classical Hamiltonian is the generator of time translations. Certainly, the quantum Hamiltonian, I mean, in some sense, we shouldn't have to ask. Well, there's a certain point of view, let's say, in which we don't have to ask what the quantum Hamiltonian is, because it's an operator that corresponds to a measurement, and the measurement is that of energy. So as far as that goes, all we have to do is measure energy, and in principle, using the postulates, we can work out what the operator is. Nevertheless, to know what the operator is in a specific system, a strategy for not obtaining it, but for guessing it, is to work on the classical model, and then to take the classical Hamiltonians and to, in effect, quantize them and convert them into quantum operators. Simplest case is one of a kinetic plus potential problem. The Hamiltonian is classical Hamiltonian. There's no hat here, so this is classical. P squared over 2m plus v, which we can allow to be, let's make this 3 dimensions. We may allow it to depend on time as well. This is p vector here to make it 3D. This is, of course, a classical Hamiltonian for a kinetic plus potential problem. It would then be a guess in an analogous quantum situation that the quantum Hamiltonian is given by the same formula, except we replace the p's and the x's and the h's well by operators. So notationally, that just means running through this and putting hats on everything. So this gives us a quantum Hamiltonian that we can work with. It doesn't answer the question about whether it's really the correct Hamiltonian or not in any given physical circumstance. There is one point I want to make here, which is that this process of going from the classical Hamiltonian to the quantum Hamiltonian, that process is sometimes called quantization of a classical system, converting it into a quantum system. The process of quantizing a classical system is not a deductive process, and it can never be. You can't give any rigorous rules that always work. And the basic reason is that quantum mechanics is different physics, more physics than classical mechanics. If you're moving in a realm of new physics, the only way to know your answers are right is to compare them to experiment. There is no other criterion in physics. But I bring this up anyway because there are simple rules, like just putting hats on operators. That's called canonical quantization, very simple rule, which oftentimes work to some approximation. In addition to this, in the last 20 or 30 years or so in the mathematical world, if those any of you are into that, there's developed a field called geometric quantization, in which mathematicians take a classical Hamiltonian and then they find what they consider to be the most geometrically or most mathematically natural or compelling method of converting it into a quantum Hamiltonian. And this has been very useful for representation theory and a lot of other stuff. It's really quite a useful piece of mathematics. But it is mathematics and it's not physics. And in physics, if you want to know what the quantum Hamiltonian is, you ultimately have no hope, no recourse, but to ultimately to appeal to experiment. But in any case, let's say that by this this canonical quantization procedure, which I just carried out here, it at least is a guess for what the quantum Hamiltonian is. So let's go with it and see what it implies. So let's suppose we take this as the quantum Hamiltonian. In this case, the Schrodinger equation looks like this. We have h hat psi is equal to IH bar d psi dt. This is in Ket language like this. If I take this and multiply by a bra x like this, position eigenket, on the left-hand side, I get x like this. And for this Hamiltonian, it's going to be p hat squared over 2m plus v of x hat, x vector hat, might be a time dependence. And then we've got psi on the right-hand side. So that's the left-hand side here turns into that. As far as the potential is concerned, the x hat operator, we can let it act to the left on an eigenbra of itself, and it just turns it into the C number, and thereby we can just drop the hat. If we do, then this operator is now being just a C number, can be taken out of the matrix element. Okay. As far as the momentum is concerned, on the other hand, recall the rule I specified earlier that the P vector, when we remove it from the matrix element, it has to get replaced by minus IH bar gradient. So when we take this thing out, move it to the left, it becomes minus IH bar gradient quantity squared divided by 2m. And the result is that this thing becomes minus IH bar squared over 2m del squared, plus the potential V, which depends on X and psi. No hats on this now. This whole thing acting on what's left over is X psi. But X psi is the wave function. It's psi of X. Actually, it depends on time in general as well, like so. You see, this del operator here only acts, it's a differentiation with respect to X. That does nothing to the ket psi. The ket psi doesn't depend on X. What depends on X is bra X here. So that differential operator acts on the bra X, but that's otherwise the X dependence of the wave function. So we start to see the usual Schrodinger equation. And then the right-hand side, by multiplying X bra times this right-hand side, gives us IH bar, partial with respect to T of psi of X and T. And in this manner, we recover the familiar Schrodinger equation as a differential equation. So I went through this partly because I wanted to show you, these tricks that are used for converting Ket language or state vector language into wave function language and obtaining the usual differential equations. Let's continue with this kinetic plus potential Hamiltonian, except let's just make it 1D. Let's go back to 1D. So the Hamiltonian then is p hat squared. In fact, let's do it this way. I'll omit the hats. 1D, just for notational simplicity, let me omit the hats, but this is quantum mechanics now. H bar squared over 2m plus v of x. I can make this v of x and t, it doesn't matter. Let me just make it v of x, it'll be enough for what I want to do. Let's just do a one-dimensional kinetic plus potential Hamiltonian, but this is now quantum. Moreover, let's do this in the Heisenberg picture. Let's work out the equations of motion in the Heisenberg picture. So this is going to be x dot. I'll omit the h subscripts here on this, but it's understood these operators are now all in the Heisenberg picture. So x dot then is equal to 1 over IH bar times the commutator of x with a Hamiltonian. Now x commutes with the potential energy because x commutes with any function of itself, but it doesn't commute with the kinetic energy. So this is 1 over IH bar, the commutator of x with p squared over 2m. And that's a straightforward commutator to work out. And if you do, you find it's just equal to p over m. Likewise, p dot is 1 over IH bar, the commutator of p with the Hamiltonian. Now the momentum commutes with any function of itself like the kinetic energy, but it doesn't commute with the potential energy. So this is 1 over IH bar with a commutator of the momentum with the potential energy V of x. And if you use the rules for commutators, this turns into minus V prime of x. All right. So those are the Heisenberg equations of motion. Let me summarize them here. In the Heisenberg equations of motion, we've got x dot is equal to P over m. We've got P dot is equal to minus V prime of x. Now I'm omitting the 8 subscripts and I'm omitting the hats, but of course these are operator equations. Now on the other hand, if we take the classical Hamilton's equations, we'll associate these with the names of famous people. In the classical Hamilton's equations, x dot is dH dP, which is equal to P over m. And P dot is equal to minus dH dx, and that's equal to minus V prime of x. So we obtain classical Hamilton's equations of motion, and lo and behold, they're the same form as the Heisenberg equations, exactly the same form. The difference being is that in the classical equations, these are C numbers, and in the Heisenberg equations, they're operators. But it's striking the similarity between them. Now then, let's take these Heisenberg equations of motion and let's form expectation values. We're working in the Heisenberg picture, so I'll take a bra and a cat, which are both in the Heisenberg picture, and let's sandwich it around both sides of these equations in the Heisenberg picture up there. Let's just do this both sides of the equation. Let's take the x dot first of all. Let's take psi Heisenberg sandwiched around x dot, and I'll put a Heisenberg subscript on now to remind ourselves that's really in the Heisenberg picture. This is what we get for the x dot part of this sandwiching that we get. Now in the Heisenberg picture, the only thing in these three objects you see here that depends on time is the x, because operators in Heisenberg picture depend on time. The psi h's don't. So this is the same thing as ddt of psi h sandwiched around x Heisenberg without the dot. However, as I explained earlier, these matrix elements are the same in both the Heisenberg and in the Schrodinger picture. So this is the same as psi Schrodinger, x psi Schrodinger. It doesn't matter which picture we evaluate the expectation value in. So let's just abbreviate the notation and call it ddt of the average value of x. That's what that is. So that's what we get on the left-hand side here. Now sandwiching psi h around the right-hand side, m is just a constant, so we get the average value of p. So by taking expectation values, we get ddt of the expectation value of x in either picture is equal to the expectation value momentum divided by mass. That's from the first equation. And likewise, from the second equation, we get ddt average value of p is equal to, with a minus sign, the expectation value of v prime of x, like so. And these are relations which are derived from the Heisenberg equations of motion, and they fall under the name of Ehrenfest. Ehrenfest relations involve relations among expectation values. To go back a little bit, the contrast between Heisenberg and Hamilton was that Heisenberg has equations of motion which are operators, and Hamilton is that they're C numbers. However, now by taking expectation values with respect to a definite state vector, psi h, we've converted the operator equations, the Heisenberg equations, back into C number equations, which now are associated with yet a third name, namely Ehrenfest. So now we have two systems of C number equations, here and here. And the question is, are they the same? If they were the same equations, what it would mean is that expectation values follow a classical orbit, you see. However, these equations are not the same. And the reason is because this is minus v prime of x, and this is the expectation value of that, where this is really the x operator here, so it gets under the expectation value sign. That's what that means. You see, if I were to take the classical equations of motion and replace x and p by the average value of x and p, I would get equations of motion in which the average values follow the classical equation of motion. But that would give me, for this term here, not minus average value of v prime, but rather minus v prime of the average value of x, like so. And these two things in general are not equal to one another. And thus what we see is that the Ehrenfest relations are interesting, but they do not tell us that expectation values follow the classical orbit. In fact, they don't follow a classical orbit because of this v prime of x term here. Now, I sort of warn you about that because there are people that run around and say, oh, Ehrenfest says that wave packets follow a classical orbit. You'll hear people say that who haven't really thought it through very carefully. It isn't true. They don't. It doesn't say that. However, having given you all those warnings, on the other hand, it is true that under certain circumstances, the Ehrenfest relations do tell you that the wave packet follows the classical orbit at least approximately. And I'd like to explain the circumstances under which that's true. So let's take a wave function as a function of x psi of x like this, and let's sketch it. And let's assume the wave function is localized. It doesn't have to be a Gaussian, but let's suppose it's localized. And it's localized, it's got some expectation value. Let's call it x0 here. So x0 is the expectation value of x, like so, with our wave function psi of x, which is given here, like that. We can call this a wave packet. I've noticed that in the literature, nobody ever defines what a wave packet means, and then sometimes although they don't say what they mean, you can kind of tell it. And what they mean is not what I would call a wave packet. What I call a wave packet is a wave function that is localized and looks something like that. It doesn't have to be Gaussian, it just has to be localized. It's mostly concentrated around the expectation value of x. So let's call that a wave packet for our purposes here tonight. Now let's suppose we have such a wave packet. Now let's consider a function which is a slowly varying function of x. Or let's, to be more specific, let's say it varies slowly on the scale length of the wave packet. Over the dimensions of the wave packet, the function f is, it's almost constant, or a Taylor series expansion gives you a good approximation. And then let's consider the expectation value of this function f of x with respect to the state psi of x, like this. So this is just the average value of f, like this, is equal to this, with respect to such a state. Now, the only parts of the x-axis that matter are the parts near x0, and in that range, f can be well approximated by a Taylor series. So let's write this as f of x0 plus x minus x0 times f prime of x0 plus higher order corrections, quadratic corrections. Now, if you look at this formula here, replacing f by f of x0, the f of x0 is a constant. It's independent of x, can be taken out of the integral. What's left over is a normalization integral, which is just 1. So the first term of this is just equal to f of x0. As far as the second term is concerned, the f prime of x0 is another constant, and again can be taken out of the integral. What's left in is x minus x naught. Well, the x does depend on x, but when you integrate against psi average value squared, what you get is the expectation value of x. But the expectation value of x is x0. So this term actually cancels when you do it under the integral. So you get a plus 0 here. So in other words, through first order, if you have this kind of a picture here, through first order, the average value of f of x is equal to f of the average value of x. And now if I take f and replace it by v prime of x, replaced by v prime, the first derivative of the potential, then what you can see is that these two things, which are not equal to one another, in fact are approximately equal to one another if the wave function is a wave packet like that. And so the result then is that the Ehrenfest relations, which are exact as I've written them here in the box, if the wave function, if the state vector psi, that is to say the wave function in question, is a wave packet in the sense that I've been talking about, in the sense this picture conveys, then the expectation values actually do follow a classical orbit, at least to the neglect of these second order terms here. Now in practice, now this is important because this gives us a link between quantum mechanics and classical mechanics. It allows us to understand in some sense how the classical limit emerges from quantum mechanics. It's one reason I'm giving attention to this particular analysis. All right, now On the other hand, it's important to remember that wave packets don't stay wave packets, they spread over time. And so even if the center of the wave packet was expectation value was following a classical orbit for some period of time, after a while, the real wave packet is going to spread so much that these approximations that I made here are not very good. And so this whole scheme is going to break down after a while. And after some period of time, it will no longer be true that quantum expectation values follow a classical orbit. Okay, having said that, and having made all these warnings then, there's one further proviso that I want to make, which is that in the special case in which the potential is a quadratic function of x, then it turns out this can be replaced by an equal sign, that these two things actually are equal. And this is easy to see, because if the potential is quadratic in x, then v prime of x, this is just in 1D, but it'll give you the idea. If v is quadratic, then v prime is linear in x, so it's ax plus b. It has to look like that. And so v prime of the expectation value of x is equal to a expectation value of x plus b. But that's the same thing as the expectation value of ax plus b. And so in that case, this inequality up here can be replaced by an equality. And thus we see that if the potential is at most a quadratic polynomial in the position x, then the expectation values of the wave function do follow the classical orbit. And moreover, in this case, there is no requirement that it be a wave packet. It's not an approximation at all. You could have a linear combination of wave packets, one here and one in San Francisco, so the average value is halfway in between, and had nothing to do with the values of the potential at the two endpoints. And it would still be true that you'd follow the expectation values would follow the classical orbit. So that's a special case for quadratic potentials. And by the way, that includes not only the free particle, but also a particle in a uniform gravitational or electrical field where the potential is proportional to x. And of course, it also includes the harmonic oscillator. It actually does more than that, although I won't prove it here. It turns out that if the Hamiltonian, the whole Hamiltonian, including the kinetic energy, is a quadratic function of both position and momentum, q and p, in other words, together, even possibly including cross terms like xp cross terms, then it's still true that the expectation value follows the classical orbit exactly. So those are some aspects about the Ehrenfest relation, which is related to the classical limit. Now, a more sophisticated way of understanding the classical limit is to do WKB theory, and we're going to do that in an upcoming lecture. But right now, Ehrenfest gives us a taste of the classical limit. I've got a few minutes left, and the next major topic is to generalize this kinetic plus potential Hamiltonians to include magnetic fields. And so let me just make a beginning on it by just reviewing some facts about electric and magnetic fields in classical electromagnetism. The equation of motion of a charge, this is now classical mechanics again, equation of motion of a charged particle in an electric and magnetic field is that the force, which is the mass times the acceleration, is given by an electric force plus a magnetic force. So it's QE for the electric force, and it's Q times V over V cross B for the magnetic force. And by the way, I'm using Gaussian units here, which is the reason for the C factor that you see here. In any case, that's the equation of motion. And this is the obvious place to begin if you want to look at orbits in electric and magnetic fields. And the equations of motion are expressed purely in terms of the electric and magnetic fields. It is a curiosity, however, that when you want to do a Lagrangian or Hamiltonian formulation of the problem, even in classical mechanics, you can't express it in terms of the electric and magnetic fields. You have to express it in terms of potentials, of which there are two. There's the scalar and the vector potential. So the electric field is given by minus the gradient of phi minus 1 over c dA dt, where phi, I'm using capital Phi for the electrostatic potential and A for the vector potential, and the magnetic field is given by del cross A. And so as I say, the Lagrangian and Hamiltonian have to be expressed in terms of phi and A. Now, the thing about the potentials phi and A is that they are not unique. They can be subjected to what we call a gauge transformation. If I replace A by what I call A prime, which is equal to A plus the gradient of F, where F is a function of X and T. And then I simultaneously replace phi by phi prime, which is phi minus 1 over C dF dt, like this. Then the new field, the new potentials A prime and phi prime give the same electric and magnetic fields as the old ones do. That is to say, E is equal to E prime and B is equal to B prime. They don't change under this transformation, which is called a gauge transformation. But the potentials do change. This F, by the way, is what I'll call the gauge scalar. This is the scalar which induces the gauge transformation. I'm assuming you're familiar with all of this from your course on E&M. But let me just make one further point, which is that there is a way of thinking about that. I think there's a certain way of thinking about this which is useful. And that is to say that the E and the B fields are physical because you can measure them, and they're what appears in the equations of motion. The potentials A and phi, however, are not physical. They're not completely physical. They're partially physical, but because by carrying out these derivatives here, you can compute the physical E and B from them. But they're not completely physical because you can change them, and it doesn't change the E and the B. So the A and the phi have both a physical part and a non-physical part. And the non-physical part is the part which is changed by a gauge transformation. Okay, that's all I want to say for tonight, but that's a lead up into where we'll start in the next lecture, which is having to do with the fact that in classical Lagrangian and Hamiltonian mechanics, as well as in quantum mechanics, it's necessary to use the potentials in the Hamiltonian rather than the electric and magnetic fields, and we'll see some of the consequences and ramifications of that fact. All right, so that's all for tonight. Are there any questions?
Yeah, actually, I was wondering earlier when we were talking about the Heisenberg versus Schrödinger picture.
Yes.
You were saying that the Heisenberg picture treats time and space at an equal footing. So I was wondering if you could elaborate on that.
Let's wait till we do field theory next semester. You'll actually see it in the electromagnetic field. I'm only doing the non-relativistic theory here, but in the relativistic theory, the Heisenberg picture is needed to establish relativistic covariance. If you work you don't want to work on a Schrödinger picture in field theory, or let's say that you can do it, but it's not the most attractive thing to do.
I see. Okay.
Are there any other questions?
Yeah, so can you talk a little bit about what you mean by like something being physical? Because like, for example, the Aharonov-Bohm effect says that like the potential is kind of at least sort of physical in the sense that like you get an effect from the potential.
Yep.
So what do you mean exactly?
We'll talk about the Aharonov-Bohm effect in some detail later on. By physical, I mean, can you measure it? And
Okay.
you can measure electric and magnetic fields, but you can't measure phi and you can't measure A. There's no such thing as a vector potential meter. The scalar potential, of course, is the voltage, right? And you might say, oh, well, we have voltmeters, right? Yeah, we do. We have voltmeters, but they have two wires. And what they measure is the relative voltage between the two wires. And moreover, it's only meaningful in the case in which you're in an electrostatic approximation where time dependence the effects of time dependence are very small. So so you see, there is no one wire voltmeter, and that such a thing doesn't exist.
Okay, sure.
Okay.
Yeah.
All right. Any other questions?
Yeah, so the Bohm effect it shows that, you know, the potential has effects on particles. And so is this too indirect of a measurement to be considered physical?
Yeah, let me answer that the same way I answered the earlier question, which is hold your horses. We will get into that in a lecture or two. or 3. We'll get to it. We'll talk about the Harnaff-Bohm effect. It turns out that in the Harnaff-Bohm effect is that all physically measurable effects are gauge invariant.
Great. Okay, I'll hold them.
Any other questions?
I have a question again about like the Schrodinger picture, where you said that the states are time dependent and the operators can be explicitly dependent on time. But like, could you explain how that's different from like the interaction, like Dirac picture, where I thought that was where the operators are time dependent and the state vectors?
Yeah, so you're speaking of the interaction picture, which is intermediate between the Heisenberg and the Schrodinger picture. And I'd rather not talk about that now because we'll get to it when we need it, which is in scattering theory. But
Okay.
roughly speaking, in the interaction picture, in the Heisenberg picture, you strip off the time evolution due to the whole Hamiltonian. So that's why the states don't evolve. In the Schrodinger picture, you strip off only the unperturbed time evolution.
Okay.
That's quite relevant, you see, in scattering theory, because if you're sending a wave packet against a target, when the wave packet is far away from the target, it's evolving according to the free particle Hamiltonian because it's not close to the potential yet. So stripping off the time evolution due to the unperturbed Hamiltonian, actually, if you're far away from the target, strips away all the evolution. And so you don't have to worry about the asymptotic limit of the state coming in from t equals minus infinity. In the interaction picture, there's really only one state and it's time independent up until the point where the wave packet starts to interact with a potential. And then it does change. This leads to the concept of the S matrix. We'll talk about that later.
Okay. Thank you.
All right, any other questions?
Yeah, actually another question. I think earlier in the lecture, when we were talking about time evolution, and we compared kind of by analogy, like the Poisson brackets in classical mechanics and the commutator in quantum. So
Yes.
we were trying to find basically what the omega operator was, and then we basically said that it was related to it was proportional to the Hamiltonian by the h bar. So I was confused about, like, you said that that h bar is the same h bar as what we had previously.
Yes.
And I wasn't clear about what the explanation was for that.
Well, because one of our formulas says that P equals H bar K, and the other one says that the energy E is equal to H bar omega. And you can see K and omega for a free particle anyway transform as a 4 vector under Lorentz transformations. And that's just because energy and momentum transform as a 4 vector. Well, if you have two 4 vectors that are proportional to one another with some factor, let's call it H bar, it had better be the same H bar for all 4 components. Otherwise, they can't both be Lorentz vectors.
But if
there's an argument from relativistic covariance that argues that those H bars have to be the same. Now, I'm not going into detail because we're not actually doing relativistic quantum mechanics here.
Right. So I was thinking, if we're not doing relativistic quantum mechanics, then how do we use that relativistic argument to?
Because relativity is correct, and non-relativistic quantum mechanics is a limit of it. That's why. Okay. Please don't be shy to ask questions. I'm glad to get questions from a couple of people, but I think there may be others that have questions too. Don't be afraid to ask. Are there any more questions? Well, if not, then I will do the usual and stop screen share. And I will then stop recording.